Hello and welcome back to part 6 of neural networks from scratch in C++. So in the last video, we sort of gave a hand-wavy description of what a cache is and why the original matrix multiplication that we wrote was naive. But now I want to be a little bit more specific. And by a little bit more, I want to be a lot more specific. Okay, so we were talking about this thing called a cache. And a cache is a small memory, but it's very fast. So if you want to read from it, it's incredibly fast compared to reading from, say, main memory, which I'm going to draw as a block over here. So here's our main, and here is our cache memory. So let's say that I initialize a matrix at the beginning of a program. So I'm going to initialize my matrix. And this matrix is going to be initialized here in main memory. So of course it's going to be 0, 1, 2, just like our A range matrices. 0, 1, 2, 3, and let's say some more data that comes later. Okay, so this is what our matrix looks like in main memory. So what happens is when I reference this array at this particular address, we don't actually try to read from main memory first. We try to see, does the data that starts at this address, or is this address in any way contained within my cache memory? And at the beginning of your program, this data is not in cache, it's in main. So what you do is you have to fetch the data. So I fetch this data and I put it into my cache. So this is called a cache miss. And the miss triggers a pull into the cache. So now I'm going to draw my data as if it's on the side like this, and I'll explain why in a second. So 0, 1, 2, 3. And then dot, dot, dot. So now anytime I want to read this data now, what's going to happen is, because of the fact that it's in the cache now, I check, see whether it's in the cache. Well, yes it is. And I get a hit. And this is much faster than reading from main memory. Okay, so let's go back to the matrix multiplication example. So here's a matrix, another matrix, and our output matrix. So why was this matrix multiplication so bad? Well, over here, this data, remember, it's stored contiguously as if it was row major. So we go along a row, and then the data that follows comes over here, etc. And all of our matrices are stored in this fashion. Okay, and I sort of lied to you. In the last video, I was saying that we pull an entire row into the cache, which is not necessarily true. So this is why I'm going to bring up this idea of a cache line. Okay, so let's say that we have a 128 byte cache, and we have a cache line size of 64 bytes. How many lines do we have? Well, the way that you do it is you divide the total size divided by the size per line, so 128 divided by 64, you get 2 cache lines. So what is a cache line? Well, the idea behind a cache line is this is the unit of data that we pull into the cache at once. So we always pull, so say I started over here, this is the address and I got a miss, so I pull in a cache line, and I pull in 64 bytes because that is my cache line size. So in our examples, we were constantly using integer data formats for our types. So integers, they're 32 bits, which means that they're 4 bytes. And if you divide 64 by 4, you get 16. So you get 16 elements per cache line. So in this case, we would pull from 0 all the way to 15 because that's our A range. So our final value here, assuming this was our cache line size, that would be 15 over here. Okay, so that means that, let's say that I'm pulling from my first matrix. At the beginning, I'd be pulling in 64 bytes. Okay, and this is actually not bad because the first matrix, we want to get rows, and it's already in row major order, right? But in our second matrix, remember we were talking about how we're pulling in 64 bytes, but then we're going to be iterating over the column. So we're going to get a cache miss, pull this in, but we're not going to be reusing any of this data. We're just going to now go to the next line, and we're going to pull this entire line just to use one entry in the line. And if our matrices were really small and our cache was big enough, potentially we could store all of the inputs and outputs inside the cache, and we'd always like ensure that eventually we'd keep getting cache hits, right? But the problem is, in this case, like let's say that we had big matrices, well, we'd obviously eventually get cache misses, because what's going to happen is, like let's say that we have a space for 2 cache lines. Well, once you get a miss, you pull in a line. Then let's say you get another miss, you pull in a line. And then what's going to happen is, well, we ran out of space. So what do? Well, we need to replace one of these lines. And the way that you do it is you replace the least recently used. So in this case, we use this one first, then we use this one. So the least recently used would be the very first one, because the second one we used more recently, right? So now, if you need to pull in another line, you essentially overwrite this cache line. Okay? So the reason why we want to write cache-friendly algorithms is because it's going to make it a lot more performant, right? So now let's try to talk about how can we actually make this more performant. I was just doodling over here before. I'm just going to delete this so as not to introduce confusion, and let me now introduce this topic. So let's try to make this more performant. So our very first one, we were talking about how this matrix is it already seems like we're doing the right thing, right? Whereas our second matrix, what if we were instead of having this matrix be in memory stored in row major fashion, what if it was in column major fashion instead? So let's make some small matrices. So let's say that this is our first matrix, and we want the first matrix to be in row major. So now in memory, that means that we'd have 0, 1, 2, and then 3 in memory. Okay? And when we reference this address, well, let's say that we had a cache line of 8 bytes. Then we pull in the 0, 1 into the cache. Right? So now let's say that we also have 0, 1, 2, 3 as our second matrix, but instead we store it column major in memory. So instead of going across the row in memory, we go across the columns in memory. What that would look like is 0, 2, 1, 3 in memory. So they're the same matrices, it's just that in memory we store them differently. So, but mathematically they're the same object, right? So now here's our output, 0, 0, 0, 0. And for the same reason as before, we want to make sure that we don't iterate over the output in column major fashion, right? So a way that we can do that is we can instead iterate over the rows, and that means that we would be moving, we would have to change our matrix multiplication algorithm slightly. So let me explain what I mean by that. Okay. So let's say that here we fetch the first row. So now we put this into the cache, into our cache. And then we go over this column. So now we put that into our cache. So now we have a row and a column in our cache. We compute the result, and we want to store it somewhere. Well, we're going to store it in this row, right? Well, we really want to store it in the pixel, or the first entry of this row. So we would be storing 0 times 0 plus 1 times 2. So we would be storing 2. So what we do is we fetch this row, and we also put it into the cache. So let me actually draw that. So you reference the first row, you pull it into cache, and I'm just making it simple with 8-byte cache lines. Then you get 0, 2, and you pull that into the cache. Then you pull 0, 0 into the cache. And what we want to do is we want to store the output over here to replace the first 0. So what we're going to do is there are two different ways that this can happen. So either you have something called write-through cache update, or write back. So write, I'm just going to put like ... back. So there are two different ways that we can update the cache. So the problem with doing an update here is, so we want to store, let's say, 2 in our cache because it's like super fast writes and reads into this cache. So we store 2 over here. But the problem is that, remember, we pulled this from main memory, and our main memory, the value was initialized here as like we have 0, 0, 0, 0. So right through, what happens is that every time you do a cache update, you also need to update the value in main memory. And this could potentially be quite slow. The reason why you do this is because, well, now if I want to do a read, I at least get to have fast reads from my cache if I ever need to read this row again. But I need to update main memory to make sure that the cache and the main memory are consistent with each other. So that's write through. Then there's write back. And the idea behind write back is that you only update the cache, and then under very particular situations, so say we have an eviction or something like that, or under a particular interval, you have a timer that goes down, and every time we have any mismatches, then the idea is only then we do an update back to main memory to make sure that the cache and the main memory are consistent. Consistent. So you can see how having us iterate over the rows in the output really, if we have a write back mechanism, this is like super ideal, because if we have a write through mechanism and we need to update main memory every single time, obviously it doesn't matter that we're storing the output in a row major fashion, right? Okay, so let's go back to this example. So now let's say that we have a write back mechanism. We update this value in the cache, okay? And now, because of the fact that I'm storing my output in row major, it would make sense for us to now move to the next column in the second matrix. And what we're doing is we're keeping the very first row fixed. And now where would the output go? Well, the dot product between this and this is going to go over here, right? So let's do that. So we have 0 times 1, 0, plus 1 times 3, 3. And then we would update our cache over here under this write back strategy. Okay, so what is beneficial about this approach? Well, what's beneficial is over here, we've achieved spatial locality because of the fact that the next data that we want to write into is next to the previous data that we wanted to write into, right? So we achieve some spatial locality here. But what's also nice is that we've achieved something called temporal locality. So temporal locality being the reason that we achieved this is because we kept this row constant and we kept this row in the output constant. So because of that, we're guaranteed that it's going to be in the cache. We got a cache hit on the 0, 1. We also got a cache hit on the output row. And while we don't achieve temporal locality on the middle matrix because we've just moved from one column to the next, by having it be in column major order, we've achieved spatial locality. And here we have, well, we have spatial and temporal, and here we have spatial and temporal. So hopefully that gives some intuition as to how we can very easily improve the original naive matrix multiplication. And in the next video, I want to actually write out the code for how this is done. All right, hope to see you there.